Hey everybody! Before we get started today, a little problem for you to work on some scratch paper. Don't do this in your notebook. This is just a scratch paper problem, but it'll kind of get your brain running on what we learned yesterday and thinking about how we can apply it for real today. So pause here, give this problem a couple of minutes of work, see what you can come up with, and then again do that on scratch paper and we'll begin after that. Alright, so now in your math notebook, today I want to teach you how to think about and solve problems involving diameter and circumference. So please make that the title on the next 3 pages in your math notebook, and then mark it, close it, think, and unpause. Alright, so yesterday we talked about circumference and diameter. Remember, in a circle, the diameter of a circle is the distance across the circle, from one side to the other through the middle. I didn't draw it perfectly straight, but should have. That is called a diameter, often abbreviated with a lowercase d in geometry. And then we also talked about circumference. That is similar to perimeter, but for a circle. It's the distance around the outside of the circle, if I had drawn that perfectly. That's called the circumference, often abbreviated with a lowercase c in geometry. And we figured out that those are related yesterday. We figured out if I took that diameter, it would fit 1, 2, 3, and a teeny bit more times around the outside of the circle every time. Or, if you want to think about it the other way, if I took the circumference and I cut it into diameters of the circle, same thing. I would get 1, 2, 3 full diameters, and then one more teeny little bit left over. So we could say either the circumference is the diameter times, we called that number pi yesterday. It's 3, we usually approximate it at 3.14, but it's really a never-ending decimal that goes on and on. So we could say the circumference is the diameter times a little more than 3. Or I guess we could reverse that and say the diameter is equal to the circumference divided by that pi, a little more than 3 number. You're usually going to see this one, but it can go either way. So that is all that we kind of learned yesterday. So on to this problem you thought about. This is an application of that. So wind turbines are devices that turn mechanical energy into electrical energy. The blades on the wind turbines below are 24 meters long. So this is 24 meters long. Says a turbine can create about half a watt of electricity for each meter the edge of the blade travels. So that means, like, as this moves 1 meter, we would get half a watt of energy. And then as it moved 1 more meter, another half a watt of energy, and so on. So that blade's going to move like around, and all in all, obviously, it's going to travel in a circle. So that's why I kind of brought it up, is it's an application of a circle problem, and I kind of want to know how much electricity would one rotation around the turbine produce. So to know that, I have to know how far it is around the turbine. How many meters is that around the turbine? That's what I want to find out, and that involves me finding the circumference of that circle. So to do that, I learned yesterday, and as we just reviewed, the circumference is equal to the diameter of the circle times pi, times a little more than 3. So if I knew the diameter, I could multiply it by a little more than 3, and I would know how far around it goes in one trip. So, I don't have the diameter of the circle, you'll notice. It would be easy to rush and say, oh, 24 must be the diameter because they gave it to me, but it's not. If you'll look, that's only half the diameter. That only goes from the middle to the outside of the circle. So the real diameter would have to go all the way across. That would be the same as that, another 24. So all in all, the diameter is 48 meters, not 24. Now I'm ready to find the circumference. So if I know that the diameter is 24 meters, I can multiply, if I know the diameter is 48 meters, as I just found, I can multiply that by pi, and I'll know the circumference. I'll know how far around it goes in one trip. So let's find that. 48 times, I'm just going to approximate it, 3.14. Your calculator might have a pi button. Some of them do. So you can get an even more precise version of that with a longer decimal. But I'll say it looks like the circumference is about 150, well, almost 151 meters. So, not actually done yet. That's how far it travels. I want to know how much electricity it would produce, right? So I'm close now. Now I know it travels that far around. And it says here for each meter it travels, it produces half a watt of electricity. So I need, rather than producing a whole watt per meter, it produces a half a watt. So this is how many meters it travels. So a couple options. I could, since it only does half a watt per meter, I could divide that by 2, or I could multiply that by 0.5. Those are going to be the same. Hard to do decimal and this multiplication sign. Times half or divide by 2. Either of those are going to give me the same thing. They're going to give me about 75.36 watts. Is that a lot of electricity? It is not. Unfortunately, that's one of the reasons wind electricity is not more common, is that 75,000 watts in one turn of the turbine. One house in the United States on average uses, I think, 48,000 watts a day. So it takes a lot of turns of the turbine to even fuel one house for one day, if this number is correct, if I'm remembering it right. So that is a circumference problem. You'll notice there was a lot to it. I had to consider a whole lot of things and not just plug numbers in like real fast. Let's try one together. Open your math notebook and let's talk about tracks. You don't necessarily have to write this first part. You can just know this first part. I think it's interesting. If you ever watch any kind of track racing, you know, the runners on the outside start way ahead of the runners on the inside because their lane is farther. Like to go around this wider circle, they have to go a lot farther than the person running this narrow circle. So they stagger the race and they let the person in the inside lane start farther back and the person in front. They both end up running the same distance. It's just since the lanes are wider, it works that way. So again, you don't have to write that. I just want you to know that. So on the track to the right, how much farther would a runner in the outside lane run than the runner in the inside lane? So go ahead and copy that down and unpause when you're ready for us to work it. So if a runner on the inside lane were to run this, they have to run around a circle with a diameter of 100 feet. They would run, I'm sure, as close to the inside as they could. And they would have to run this smaller circle. And so that runner would run that circumference of the small circle. So the small circle has a diameter, I'll say small circle has a diameter of 100 feet. So how far do they run that circle? That's a circumference. The circumference is equal to the diameter times pi. And that is 3.14, multiplying by 100, not too far. That would tell me that on the small lane, the runner runs about 314 feet. I always say about with pi because I am rounding it. So that's how far the runner in the shorter lane would run around this circle track. What about the runner running around the larger lane? They have to run farther. This notation says it's 5 extra feet to get to the next lane, but you'll notice that actually doesn't just add 5 feet to the diameter. It actually adds 10 feet because we've got to add the 5 here and the 5 here. So actually they end up running around a circle with a diameter of 110 feet, not 105. So they're running around this larger circle and they actually have to run farther. So if you ever race somebody around a track, take the inside lane, it's shorter, gives you a big advantage. So this person's actually running around a bigger circle in that outer lane. Their diameter is 110 feet. So same formula. how far they run, that circumference, that's equal to 110 feet times pi. That one I am going to need my calculator for. 110 times 3.14. So they're running actually quite a bit farther. 345.5 feet. Was it a half? Almost. 345 and 4/10 feet. Look, I mean, they really, just for that little 5 feet difference, that's not that far. They run way farther. I mean, way farther. The difference is pretty substantial. 345 and 4/10 minus 314 is 31 more feet. Pretty surprising. That's a pretty big difference, you know, in a race where everybody's pretty fast, like in the Olympics or something. That's a big advantage. So that's why they let the person in the longer lane start farther ahead, so that they're equal. Y'all, those were pretty advanced problems. So if you need to check these out again, please do. Both of those involved a lot of steps, a lot of calculations, and a lot of thought to be able to solve a pretty advanced problem. Being that this is only your second day dealing with circumference and diameter, I would highly recommend watching this again so you can think through this problem now that you've solved quite a few, or you've solved two. And then once you really feel like you've got a command, like, okay, I get what's going on here, I get how these are related, I get how I calculate them, you're all set, and I'll see you tomorrow.